Alright, welcome back to Rock the JVM. I'm Daniel, and in this video I'm going to talk about backpressure in Akka Streams. So this video assumes that you know some Akka Streams foundations, at least the basic components including sources, sinks, and flows, because that's what I'm going to demonstrate in live code. That's all you need to know. I'm also going to show you a quick intro to them if you've never seen them before to get you up to speed really fast. And as always, I recommend that you code with me in this video, and whenever you need to refresh your memory about this concept of backpressure, just refer back to this video or to the written form at the blog with the link in the description. Alright, so without further ado, let me move back to my little code. So here I have a small object. I call this Akka Streams backpressure with a simple main method in case we need to test something. Now, if you want to use the Akka Streams library, you need to go to your build.spt file and you need to add your Akka Stream library. So you need to add com typesafe akka %% Akka Stream, and the version is 2.6.17. I think at the moment of this recording, any 2.6 version will work fine for this video. Even a 2.5 version will also work fine, I think. All right, so I recommend you use a 2.6 version. You can go to akka.io and get the latest version of Akka Streams. That shouldn't be that big of a problem. And I'm going to give you a crash course on the major components of Akka Streams. Now, Akka Streams is a library which implements the reactive stream specification. The reactive stream specification is a very loose document which was compiled by a lot of technical folks over at Lightbend and in many other places, which describes some asynchronous systems. And in this reactive systems, we have the concept of a publisher which emits elements asynchronously, the concept of a subscriber which consumes elements asynchronously, and the concept of a processor which transforms things along the way. So I can describe a publisher as a little element here, a little mechanism that emits elements downstream, and it's up to us to specify how those elements are consumed. So I will write another fabulous ASCII art diagram here to denote a consumer. So we have a publisher and a subscriber, and in between we also have transformers if we want to change data along the way. So our streams will start from sources, and then we have flows, and then we have sinks in the Akka Stream terminology. So this is the publisher in the reactive stream specification. This is the processor. And finally, we have the subscriber in the reactive streams, the big document specification. So this is the subscriber. Now, in Akka Streams, we call these source, the processor is called a flow, and the subscriber is called a sink. So this is what I'm going to demonstrate here. So I'm going to have a source as source that you can import from Akka Stream Scala DSL. This one, make sure you import the right type. So source applied to a local collection. So I'm going to use 1 to 1000, for instance. So this will emit all the numbers 1 to 1000 asynchronously. Pretty fast, if you ask me. Then we have a flow. I'm going to have flow that I'm going to import from Akka Stream again. So I'm going to import Akka Stream Scala DSL flow. Make sure you import the right package here because Akka Streams also has APIs for Java. Then I'm going to add the type here. So flow int.map. And then I'm going to say underscore times 10, for instance. So this will receive elements of type int, and then we'll transform them by running this function, and then it will emit the results downstream to the sink. And I'm going to describe a sink as sink dot. So I'm going to import sink, not the ZeoStream one, but the Akka Stream one. So make sure you import the right object here. So I'm going to say sink dot for each. Notice that for each takes a type, which means that the sink receives elements of this particular type. So I'm going to have for each int, and I'm going to say print line. All right, so these are some fundamental components. Now, the way that we combine these together is to say we compose a graph. This is a topology. Right now we have just a simple linear topology, but in Akka Streams we can build very complex topologies. Just to keep things simple, I'm going to say source via flow dot to sink. So this is a very descriptive API. Now, this graph is just the blueprint of an Akka Stream. No work is actually being performed. No elements flow through the stream unless we say graph.run. So when we call run, now we will start performing work. And notice that the compiler signaled an error for me. It says that we don't have an implicit materializer in scope, which is something that can allocate the right resources to run these components in turn. Now, because these are based on Akka, they run with actors under the hood, which is why I'm going to add an implicit. I'm going to use a system as an actor system. You can use either, I recommend use the typed one, so I'm going to use actor system with behaviors.empty. No messages will end up in this actor system explicitly. I'm going to call this streams system. And in order to not have the compiler throw warnings in my face, I'm going to say actor system of whatever. All right, so now that I've defined this system as an implicit, or in Scala 3, you would have to define this as a given, that'll be an equivalent way. Now the graph can run with this actor system, which will also act as a materializer. Rather, that means that these components will run actors under the hood. So if I run this application, we will see the numbers 1 to 1000 being multiplied by 10, and then the results will be printed to the console. Now I have a lot of Scala code, which is my entire YouTube channel here. It'll take a little bit of time. So notice that we have all the numbers 1 to 1000 multiplied by 10 and printed to the console. So this is a crash course into the fundamental components of Akka Streams. Now the goal of this video is to talk about Backpressure. Now, let me take a couple of seconds to describe what backpressure actually is. So backpressure is one of the fundamental features of the reactive streams specification, and it describes how the elements in a reactive stream will flow as a response to demand from consumers. So the way that a reactive stream is supposed to work is that the downstream, that is the consumer, will ask for elements from upstream, and the upstream will start to conform and publish or transform elements along the way. So if this is our little Akka stream topology, then that means the way that elements start to flow is that the sink, or the subscriber, will start to request elements from upstream. Now, because this flow sits in between, this will also send signals upstream all the way to the source before it starts to publish elements. Now, once the source receives demand, it will start to publish elements, and then the stream will start performing work. Now, in the case where the consumer is actually very fast, then all is well into the world, because the consumer is not a bottleneck in the Akka stream or reactive stream performance. Now, if the consumer is slower, then we have a problem because the consumer is the bottleneck. And so, the reactive stream specification tells us that the consumer should send a signal upstream for the producers to slow down. So in our case, if the sink is slower, it will send a backpressure signal upstream, which will also send a backpressure all the way to the source, and the source will lower the cadence of the production of elements, which will slow down the entire stream so that the consumer is able to process them. Now, this protocol is 100% transparent, so this is nothing that we need to concern ourselves about. Now, this video is all about demonstrating how the backpressure protocol is performing in some examples, and how you can control the reaction to backpressure in the case that consumers are slow, and if you still want to maintain the throughput of your system. So to that end, I'm going to define a slow consumer. I'm going to say slow sink as sink.forEach integer, and I'm going to pass a lambda here saying that for every element, I'm just going to compute the 10 billionth decimal of pi, which in our case is going to be a thread sleep, because this is the lazy way of doing that. And I'm going to say print line x, right? So this is simulating a long computation so that the sink actually starts running slowly. And I'm also going to write a flow which transforms elements by simply printing out the incoming element and leaving the element unchanged so that we can debug all the elements that go through our little stream. So I'm going to call this debugging flow as flowInt.map, and for every element I'm just going to print out, let's say I'm going to add a tag here, so have flow, and I'm going to inject my x here, and then I'm going to return the unchanged x. All right, so I'm going to demonstrate what happens if we don't have backpressure. So I'm going to run a method called demo no backpressure. And I'm going to connect my source of numbers. So source.via debugging flow, and then I'm going to say .to slow sync, and then I'm going to call run on that. There is another concept that I'm going to talk about very briefly, maybe I'll expand that in another video, which is that when you connect these components together via the via and to methods, they're actually called fused. So this is operator or component fusion, which is to say that these three components actually run on the same actor behind the scenes. By default, Akka Streams assumes that all of our little Akka Streams components are fast individually, and so instead of running them on separate actors and relying on message exchanges, if we have the transformations coming up very, very fast inside our processors, or our flows in this case, then it might make sense to compose them into the same actor so that the message exchanges do not cause additional overhead, which is why the Akka Streams components are by default fused, that is, work on the same actor. So because they work on the same actor, we're going to see something very interesting here. So I'm going to call my demo no backpressure function, and let me run this application. My compiler is hot, and so we'll have 1, 2, 3, 4, 5, 6, and so on and so forth, because we have every single element being processed from beginning to end sequentially. So every single element takes exactly 1 second to go through the entire stream. So the slow sync basically slows down the entire stream. Now this is not backpressure because the source, the flow, and the sync will run on the same actor, and this is as if I defined an actor which receives all the messages from 1 to 10 and does the debugging flow, which is printing something and leaving that element unchanged, and then doing the thread sleep and printing that out. So for every element we will have another second to run. Now, in the case that one of the components in your Akka Streams is actually slow, which breaks the assumption that the Akka Streams API follows by default, you can insert asynchronous boundaries in between any two components here so that you can run them on separate actors. So I'm going to demonstrate something else here. I'm going to demonstrate a backpressure example. So I'm going to define that as a simple method. So I'm going to have source via debugging flow. This is quite fast, so I'm going to insert an async boundary here. So I'm going to say async, which means that everything up to this point runs on one actor and everything after that will run on a separate actor. So I'm going to have to slow sync and then call run. Now in this case, if I call this one, we're going to see a different kind of output. Instead of printing the elements one by one in the flow, notice that the flow already prints 16 elements, and we have the sync printing 1, 2, 3, 4, 5, 6, 7, and 8. We have the flow getting many elements at once, and then we have the sync printing one by one, and then the flow keeps on adding more elements, and then the sync carries on with one by one. Let's interpret this output. Now, the new thing that I want you to remember is that in the case of backpressure, all the Akka Streams components, if they run on separate actors, they have internal buffers so that they maintain the throughput of the final stream, which will then be cleared once the consumer starts behaving a little bit faster. So in our case, the slow sync will force the debugging flow, because it runs on a separate actor, will force the debugging flow to buffer 16 elements, which the flow receives very, very quickly. And once the flow receives 16 elements, which is the total amount of elements that it can store by default, so every Akka Stream component will have 16 spaces by default, then the debugging flow will consider that its buffer is full, and only then it will signal a backpressure to the source. So the debugging flow will attempt to maintain the throughput of the stream by buffering elements in the meantime, and when the buffer is full, then it will have no choice but to signal a backpressure to the source, which is why it will stop producing more elements. Now the sync will do its thing, so it will print elements 1 through 8, and before the element 8 is printed, the flow will notice that half of its buffer is empty and it will start requesting more elements from the source, that demand that I was talking about. So the flow will fill up its buffer again, and when the buffer is full, it will send a backpressure signal to the source yet again, because the flow buffer is now full. Sync will carry on doing its thing, print 8 more elements. The flow will then notice that half of its buffer is full, request 8 more elements, and this will carry on ad infinitum. So the backpressure signal is transparent for us, and the buffer here will take care to at least attempt to maintain the throughput of the entire stream. Now there are some techniques, or rather there are some decisions that you can make in the case that the buffer of a component is full. And the default behavior of a buffer full is to send a backpressure signal upstream, which will slow down the entire stream. Now, there are some alternatives if you still want to maintain the original throughput from the producer. If you can't slow it down, for instance, you have to lose some data. So I'm going to demonstrate that by saying debugging flow dot, and there is a special method called buffer. So buffer, and I hate these pop-ups. So buffer takes 2 arguments here, the size of the buffer if you want to add more memory in case you have large fluctuations in the throughput, and the overflow strategy, which by default it's backpressure. So buffer with 16 and overflow strategy dot backpressure are the default arguments for every component. Now there are alternatives. So you can say, for instance, if you don't want to slow or you cannot slow down the source, you can start to lose data. So you can say drop head, for instance. Drop head will always drop the oldest element in the buffer to make room for the incoming one. So let's say that the buffer contains 16 elements. I'm going to use a round number, let's say 10. Round from the human perspective, not from the computer's perspective. Let's say that the buffer becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And let's say that the number 11 arrives at this flow. Well, in this case, the buffer is full, and so we will need to make room for this incoming element. And drop head will drop the oldest element, in this case, number 1, and make room for the new buffer, which is the number 11. Now, once the number 12 arrives, then the oldest element, the number 2, will be removed to make room for this new one, and so on and so forth. Now, in this case, if I run this application, the output will be, again, different. So notice that the flow will receive all the numbers so that the throughput from the source is maintained, and the sync will process just the last 10 numbers because in the meantime, the buffer in the flow kept replacing all the numbers until we had the latest 10 ones. So these are the last numbers that arrive at the sync, but the flow maintained the throughput from the sync. So this is one decision that you can make. You can also use drop tail, which will remove the newest element to make room for the new one. So assuming that you have the buffer 1 through 10 and the number 11 arrives, then the new element, the newest element of the buffer, will be removed to make room for this new one. So in this case, if I use drop tail, the output will again be different at the sync level. So the flow will carry on maintaining the throughput from the source, but notice that the numbers printed from the sync are not 991 all the way to 1000, but we have all the numbers from 1 to 9 and then the final number 1000. Why is that? Because at every incoming element, the newest element is removed to make room for the new one. If I get new elements, we'll always have the original 9 numbers and the latest element, which will end up being 1000, if that makes sense. Cool, so that's drop head, that's drop tail. I'm going to show you drop buffer. So drop buffer will remove the entire buffer. If the buffer is full and you will get a new element, the entire thing gets erased to make room for the incoming thing. So in our case, we will have the latest 10 numbers being printed yet again. So in this case, if we have drop buffer, we will have, again, all the 1000 numbers being printed in the flow, and at the sync level, we will have the latest 10 numbers because in the meantime, the buffer kept being replaced over and over and over again. Cool, so we have drop head, drop tail, drop buffer. There's also drop new, which will drop the incoming element. So if the buffer is full and there is a new element incoming, sorry, you don't have any space, so you'll cut it down. So we'll have nothing. As new elements arrive, the buffer will be kept intact. If it has any space, fine. If it doesn't, it will get removed. So the sync will print, in this case, just the buffer 1 through 10, because in the meantime, before a second elapses, the flow had the time to process all the 1000 elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, not 1000. So we have drop head, drop tail, drop buffer, and drop new. There's also backpressure, which is the default. So backpressure will basically slow down the entire source. So you know that one. And there's a final option that you can use, which is fail, which will throw an exception and tear down or destroy the entire stream. That's not necessarily advisable. I'd rather slow down either my throughput or start to lose some data instead of destroying my entire stream. So we have flow 1 through 10, so this is the number of elements that it can buffer, and when it receives the number 11, it will print it out, and it will not be able to push it forward because the overflow strategy is now fail, and we'll get this log line failing because buffer is full and overflow strategy is fail in the stream, whatever. All right, so these are the reactions that you can use in response to the backpressure signal that comes from downstream. So we have buffering here, and you can choose what will happen to your buffer, to your elements, if that buffer gets full. All right, so you learned a new technique with Akka Streams in this video. I hope you liked it and enjoyed it. If you did, go ahead and click the like button for me and subscribe to the channel for more videos like this. Follow me on Twitter and LinkedIn as I post fresh updates on upcoming material, and check out my website at rockthejvm.com. I have hundreds of hours of content on Scala, functional programming, Apache Spark, Akka, Cats Effect, Zio, and many other goodies. Until next time, I'm Daniel signing off.